Sunflowers. How do they even work? We conjecture ahead.
Although this is going to be weird, and it's going to be about a different.
Title of the conference was something like "Ground Truth" or "Turtles All the Way Down," and so it seems as though there's one Ruliad. I don't think it rules them all, and it might be just hyper-rulial turtles all the way down.
Yes, it's on the back of an infinite number of hyper-rulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Again, full disclosure, this is a MacBook Pro. I'm just saying. But what the heck are we talking about? All right, this is brought to us by mathisfun.com. The Fibonacci sequence. Yes, I totally copied. I didn't want to type it. Why? Because we have computers and because we can. The Fibonacci sequence is a series of numbers. 0, 1, 1, 2, 3. Oh, 1, 1 make 2, 2 and 1 make 3. It was destiny. Shout out to Tenacious D. I should have got that ready. But what's the whole point of this? Basically, and again, I probably should have brought up a 3 blue plus 1 brown video, but we just typed it into just the YouTubes, and what came up? The algorithm tends to show you what you seek. So, but basically, when you start to graph this out, it makes what's called the golden spiral. And as you're following the numbers there, it also consequently, if you have a flower or different things, basically they tend to have a Fibonacci number of seeds, petals. It's very interesting. It's also probably, depending on who you ask, around 137 and a half, something like that. But we're going to go to some other friends just because it's totally fascinating. And it may help explain what's going on. I'm just saying. And again, a lot of this is totally conjecture, but we go to our friend Arthur Benjamin. What's going on, my dude? This is a TED Talk from 9 years ago.
So why do we learn mathematics?
Because we have to.
Essentially for 3 reasons. Calculation, application, and last, and unfortunately least in terms of the time we give it, inspiration.
This is very important because, again, I really stopped understanding math like halfway through the 6th grade when my math teacher's like, you don't need to know this now, but it'll be useful later. She taught us how to cross multiplied fractions. I still don't really know how to cross multiply fractions. But I'm just saying, that's what Wolfram Alpha's for. But all I know is the 7th grade, it's like, all right, since you know how to cross multiply fractions, here are some letters. It's like, ooh, I was like, and then, I don't know, it seemed boring. Didn't really seem like I had a reason to calculate or do these things. It's literally, as he's about to let us know, because you need to use this for a test. And then I'm realizing, oh, look, upper level finance class and nuclear physics society. It's like, oh, I understand calculus. Why? Because then I have a purpose for doing it. Again, we all have a purpose in life. Continue, Mr. Benjamin.
Mathematics is the science of patterns, and we study it to learn how to think logically, critically, and creatively. But too much of the mathematics that we learn in school is not effectively motivated. And when our students ask, why are we learning this? And they often hear that they'll need it in an upcoming math class or on a future test.
Thank you, sir. All right, we're going to go to some cool stuff here. So let's...
To understand as 1 plus 1, point of numbers can be appreciated in many different ways. From the standpoint of calculation, they're as easy to understand as 1 plus 1, which is 2.
Oh,
then 1 plus 2 is 3,
numbers.
2 plus 3 is 5, 3 plus 5 is 8, and so on. Indeed, the person we call Fibonacci was actually named Leonardo of Pisa, and these numbers appear in his book, Liber Abaci, which taught the Western world the methods of arithmetic that we use today.
Wait. So, these numbers that appeared in one of the texts that basically helps set the foundation for mathematics that we're using today. Seems like a pretty smart dude. Continue.
In terms of applications, Fibonacci numbers appear in nature surprisingly often. The number of petals on a flower is typically a Fibonacci number, or the number of spirals on a sunflower or a pineapple tends to be a Fibonacci number as well.
I got it wrong, but notice the spirals. They seem to be going in different directions there. It's like you've got different articulations maybe coming together. Perhaps that could provide a clue about what's going on in our realm of persistence. Again, conjecture on my part. I am a dude on the internet. I just happen to be blessed to have spoken with some really smart people. But hey, welcome Whitechapel. Welcome Garguts. Good to see Garguts. Garguts Entertainment. There we go. I and Fibonacci are very interested. Dude, I'm assuming, dude, I apologize. But all I know is this stuff is fascinating, and we're going to get really nerdy here in just a second. We'll play a few more seconds.
In fact, there are many more applications of Fibonacci numbers, but what I find most inspirational about them are the beautiful number patterns they display. Let me show you one of my favorites.
We are pattern recognition creatures, or at least I am. That's why I say a lot of weird things a lot, just because my mind goes to there. What is the level of relevance? I may evaluate it. I don't always say it. I often do say it. That's why I don't get invited places.
Suppose you like to square numbers, and frankly, who doesn't?
Whoa.
Let's look at the squares of the first few Fibonacci
you
numbers. Okay, so 1 squared is 1, 2 squared is 4, 3 squared is 9, 5 squared is 25, and so on. All right, now, it's no surprise that when you add consecutive Fibonacci numbers, you get the next Fibonacci number, right? That's how they're created. But you wouldn't expect anything special to happen when you add the squares together.
I mean, again, it's not like if you square certain numbers that may come out from certain beautiful, in my opinion, equations that something cool might happen. You gotta establish the deep lore. I'm just saying. But, we can totally do that. That's the day. I'm going to be traveling this next week. After that, I'm going to like to start to talk to some more people and do some more interviews again. But continue, sir.
But check this out. 1 plus 1 gives us 2, and 1 plus 4 gives us 5. And 4 plus 9 is 13. 9 plus 25 is 34. And yes, the pattern continues. In fact, here's another one. Suppose you wanted to look.
I didn't even know that was a band. I am so terrible at some things. That's the thing. Dude, this is why I talk to people on the internet, just because it's like, will there be people that will correct me? Yes, that's very important. Now, the method that one goes about correcting somebody, I think we could be a little bit nicer. I'm just saying, you put the memes out there that you want. So we'll finish this up.
Adding up the squares of the first few Fibonacci numbers. Let's see what we get there. So 1 plus 1 plus 4 is 6. Add 9 to that, we get 15. Add 25, we get 40. Add 64, we get 104.
I'm not really following this that much.
Those are not Fibonacci numbers, but if you look at them closely, you'll see the Fibonacci numbers buried inside of them.
Whoa.
You see it?
What?
I'll show it to you. 6 is 2 times 3. 15 is 3 times 5. 40 is 5 times 8. 2, 3, 5, 8. Who do we appreciate?
Oh.
Fibonacci, of course.
13 is 100. Now, okay. That's cool. That's cool. Thank you, my dude. Where do we even need to show the other video? The other video it's fun. It's in the link, but apparently, when I was listening to like an hour something lecture from another math professor, some of the things that we either already covered them or some of them are claims that really. If you hold them up to a certain level of scientific rigor, don't necessarily hold because they go into like the human ratios. It's like, okay, you can kind of do that. It's like we use it for architecture. Architects use it all the time. It's like they use things close to it, but is it actually the numbers and stuff? But I see. See, depending upon the observer, you get different stuff and things. Hey, welcome, Papa. Good to see you, my friend. I think Snow's gaming or something. But yeah. There's a lot of stuff going on, but where are we going to go next? We'll go to... Oh, I had the spiral there. Well, let's go to... I should have probably kept that video going longer there because we need to get into the golden ratio. All right, we'll bring it back up because I'm a terrible human being. But no, actually, we'll just go to the original thing that we have for math is cool. But we don't need to share audio anymore. Okay. So blah blah blah. Okay, whole bunch of numbers. Yes, makes the cool spiral. The spirals found in nature. See the golden ratio on Fibonacci. Oh. Okay. So basically, once you start averaging these things together, here's the surprise. When we take any two consecutive one after the other Fibonacci numbers, their ratio is very close to the golden ratio, which is phi, which is approximately 6.18034, yada, yada. In fact, the bigger the pair of Fibonacci numbers, the closer approximation. Okay, so 2 and 3, 1/2. Okay, so he's at 1.666 repeating, looks like. 1.6, 1.625, 1.6182575. Oh, that's very interesting. Huh. Yes, and then when you go the other way, and we don't have to start at 2 and 3, you randomly choose that, and you get the sequence, yada, 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 yada. Oh, seems to keep converging. Huh. That's very interesting. We got some cool equations and stuff here. You can do different things there. Okay, that's cool. What is the golden ratio? In mathematics, two quantities are in the golden ratio if their ratio is the same as the ratio of their sum to the larger of the two quantities, expressed algebraically for quantities A and B, with A greater than B and B greater than 0. We get A plus B divided by A equals A divided by B equals the golden ratio. Greek is, excuse me, phi. Or, oh yes, that's like, oh, that looks kind of like the, what's the real physics? This is for the null set. It's a little bit more fancy. Look like a Mobius twist in there, just saying. Notice the golden ratio, the constant. Phi satisfies the quadratic equation. Phi squared equals phi plus 1. And it is an irrational number. Basically, it's rational numbers are all real numbers that are not rational numbers. Oh, that's, well, thank you. That is, irrational numbers cannot be expressed as the ratio of two integers. Okay, so basically kind of like pi or something like that. It's like, can't just use two integers. We get fancy. So we got, yep, basically phi as 1 plus the square root of 5. 5 is a pretty cool number. That's all divided by 2. That comes out to that. It was called the extreme and mean ratio. It's such a bad. I'm just kidding. By Euclid and the divine proportion by Luca Pelicilia, and also goes by several other names. But oh, you're gonna love this. I'm gonna need to put together some actual edited videos for some of this stuff because it's so fantastic. I'm not saying that's why I'm putting out some content here and right now, but it's also a reason. Okay. Oh, what's this? The imaginary golden ratio. See, I thought I did a video on this. I couldn't find it. I think I just tweeted this out at one point. So we'll play. Yes, this is an actual thing, but it's not in Wolfram Alpha. It was from well over 6 years ago, 6.5. While playing with the results of defining a new operation, I came across a number of interesting properties with little literature surrounding it. The link to my original post is here. Finding properties of the operation divided by yada 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 y, 1 over 1x plus was it 1y, and the reciprocal addition common for parallel resistors. I don't understand that thing. So basically, you go through here. You want to find a condition for that I found the ratio between x and y minus b. Oh, the golden ratio for this work. Oh. So we go through here, and we get this. Okay. So that's the golden ratio times I. The imaginary golden ratio. So 1 plus the square root of 3i, let's divide it by 2. Hey, welcome, awesome one. Thank you for joining. Yes, the After Dark. Yes, After Dark. Ooh. Just realized PC can also stand for pop. I'm sorry, I spent so much time. These different connections that you get in your head. It's pretty cool. It has many properties with the golden ratio mirrored. This form from 2011 is the only literature he could dig up. So we go to yes. So basically the golden ratio is basically was it 1 plus 1 over 1 over 1 over 1 over 1 yada yada yada, the fraction form. So I think what is it? We got Wolfram Alpha here. So where is it? The continued fraction. Oh yeah. So it's 1 over 1 for infinity. So we go to frac. I might need to reload this. Yeah, I'm gonna need to reload this. Da-da-da. We go to the fraction form. That's a lot of ones. That's a lot of ones. Like we did I'll repost the video that we did on the one another time. So the imaginary golden ratio. It's what I'm doing this wrong because I know it's come out to actually the golden ratio exactly before. I'm doing something wrong here. It's 1 plus square root divide by 2. Yeah, it should just be like negative ones. But okay, we go to the actual post. I'm trying to be transparent here. I wasn't able to get the calculation, and I'm just gonna mess up along the way. Why? Because we can. Hey, Dandelion. Welcome for joining. Yes. Math can be very sexy, I claim. But okay, here's the actual link. It's from the math. This is the link from the original dude. So or dudette, I don't know. We all know the golden ratio. Okay, that was that construction we had before. A divided by B equals A plus B divided by A. And then we can set that to, oh yeah, I probably should have just done this construction. Golden ratio squared minus the golden ratio minus 1 equals 0 divided by that, blah, 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 blah. Okay, no, that is the golden ratio. Derp. I didn't read this all. I just got to the construction down at the end. So basically, it has all sorts of interesting properties like subsequent powers of the golden ratio sum of so-called reoccurrence relation. There exists a direct relationship with the Fibonacci series, as we were discussing a wee bit earlier. It can be expressed as a nested radical, only using the number 1. I think that's pretty neat. It is the worst real number for rational approximation because of its continued fraction representing only using ones. But suppose we divide imaginary equivalent of the golden ratio. Let's call it phi I, the imaginary golden ratio. Phi I equals AB equals A minus B divided by A. So then we get it set to, maybe this is where I was getting it wrong. 1 plus or minus I, I totally did that wrong. Wait a second. No, I tried that before. The square root of 3 times I divided by 2. Yeah, it comes out to be the same. To my surprise, the imaginary possesses all the same attributes as the standard golden ratio. There's a direct link to pi and E. So the imaginary golden ratio is equal to E plus or minus pi times I divided by 3. Excuse me, E raised to plus or minus pi I divided by 3. Let's give that a shot. Let's use a particular means. Wait, what's this? Oh, I need to go back to the thingy because I'm bad. We reload. Yes, we're doing this live. That's why we have a little disclaimer. We conjecture we're hacking the universe on a MacBook Pro. But I'm clicking on the wrong thing. No, we don't need you. The hyperbolic vortex equation. We don't need you right now. Where do we go? Boom, boom. Oh, there we. Oh no, it was here. I was just bad. I was looking at other things. Okay. What's this? All third roots of -1. Number name, -1. What's this crazy construction? The square root of -1. We're taking cubic of that. All right. Yes. E to the pi I, excuse me, e raised to I times pi divided by 3. Huh. Again, maybe I'm just doing this all wrong. But the reason why I'm showing this is because apparently that's supposed to come out, at least for a construction that I learned from Thad, for the volume of the hyperbolic figure 8 knot. It's this right here. I times polylog -1. Okay, we'll click on the thing. It'll show us here. Okay. Because it's conjectured that this construction is the imaginary golden ratio. When you take 1 and you raise it to the square root, excuse me, -1 raised to 1/3. So that it leads to -1. So I'm probably getting this all wrong, but all I know is it comes out to this. I should have done more research. That number, but when we go to that number and we look at possible closed forms, what's this? 2 Giesecke constants? It approximately equals the volume of the figure 8? Hold on, wait. Oh, the Giesecke constant. VFE is the figure 8 knot hyperbolic volume. Now, I'm not saying this explains everything, but I was told that I should probably learn about the Fibonacci numbers and the golden ratio and stuff like that, because apparently it's highly important with all the different stuff and things going on. Hey, Doc Rachel, good to see you. You are awesome. But it's see, in the other video that I saw, I can understand what they're saying, Papa, but apparently when they do some generic tests of some different things, at least for rectangles and stuff, they're saying they're more attractive rectangles, essentially. Different people, it depends on the individual. It depends on the individual. If you did 8 million people, I don't know. But yes, one plus the golden ratio is pretty awesome. But yes, it's pretty cool. It's pretty cool here. Because essentially the golden ratio was, you can also do as plus or minus, or at least this one you can, because it has the ability to do a lot of real cool things. But yeah, that's all I really had right now. But hey, thank you all for joining. Peace out, everybody. If you're in a place where it's chilly, try to stay warm because it's cold outside, my friends. But take care of yourselves, everyone. Winter is here, at least in the northern hemisphere. Peace.
Have you guys checked out the Memes of Destruction's channel? He's an interesting dude. I like him.